In the part 1 of this lecture, we have seen that given a group G, which is an external direct product of G1 and G2, then there exist two subgroups G, H1 and H2 such that H1 is normal in G, H2 is normal in G, and H1 intersection H2 is identity of the group G, and G is actually the internal, G is equal to the H1 H2, that is G can be written as a product of H1 and H2. Moreover, H1 is isomorphic to G1 and H2 is isomorphic to G2. So given a group as an external direct product of two groups, that can also be written as a product of internal product of two groups. And this property we defined as internal direct product. So let us come to the definition, proper definition of internal direct product. Let G be a group. We say G is an internal direct product or direct sum of two groups H1, H2. If Hi is normal in G, H1 intersection H2 is identity element of G, and G is equal to H1, H2. This set means H1, H2 such that H1 belongs to H1 and small h2 belongs to capital H2. This is called the internal direct product. And of course this property has come from the property of, this definition has come from the property of external direct product. So it means in above as we have defined, G is the external direct product of G1 and G2, then that G can be written as the internal direct product of H1 and H2. So every external direct product is actually can be written as the internal direct product of its subgroups, and those subgroups are actually the isomorphic to the groups which we have taken for taking the direct product. Now this is the definition of internal direct product, but this definition can be restated in another way, that H1 is normal in G, H2 is normal in G, and each element of G can be uniquely written as product of elements of H1, H2. So this we can also take as a definition. The only difference between these two is that here also we are saying that any element of G is the product of elements of H1, H2. The only difference is that in the second point, that the intersection of H1, H2 is identity, and here there is one thing, that uniqueness. Each element can be uniquely written. So we have to verify that these two things are equivalent. So suppose G is the direct product of H1, H2. So G can be written as H1 into H2. Take an element G in G, then because G belongs to H1, H2, so there exists small h1, small h2 such that G can be written as H1, H2. Suppose this element has two presentation, so we also write G to be H3, H4. So H1, H2 and H3, H4 are equal. So take H3 this side and H2 this side. So H3 inverse H1 is equal to H4 H2 inverse, but this part, this element belongs to H1 and this element belongs to H2. So it means both the elements are in the intersection. So both the elements are in H1 intersection H2, and H1 intersection H2 is identity. So it means this is identity and this is identity. So H1 is equal to H3 and H4 is equal to H2. This implies each element of G can be uniquely written as a product of elements of H1 and H2. Now conversely, suppose that Hi's are normal in G and each element of G can be uniquely written as product of elements of H1 and H2. So we will show that H1 intersection H2 is identity. So it is clearly that each element of G is uniquely written as a product of elements of H1, H2. So G is equal to H1, H2. So we have to show that H1 intersection H2 is identity. So take an element H in H1 intersection H2 and suppose that is not identity. And we have assumed that each element of G can be uniquely written as product of elements. So now H1, H2 is the product. H1, H2 is an element of G, but this element can also be written as H1, H, H1 inverse, H1, H inverse, H2, because H belongs to H1 also and H belongs to H2 also. So it means one element H1, H2 can be written in this way also. Moreover, if I take H inverse first and then H, then this element H1H2 can also be written like this. So this is a contradiction to the uniqueness, and this contradiction arises due to our assumption that H is non-identity. So hence H should be identity. So H1 intersection H2 is identity. So it means now we have two definitions for internal direct product of groups. One definition is Hi is normal, H1 intersection H2 is identity, and G is H1H2. And another definition, Hi is normal in G, and each element of G can be uniquely written as product of elements of Hi. Now, in observation 1, we have shown that given a group to be the external direct product of G1, G2, G can be written as the internal direct product of H1, H2, and moreover, Hi's are isomorphic to Gi's. So any external direct product can be thought of as internal direct product. Now think conversely. Suppose G is internal direct product of subgroups H1 and H2. We can also think G to be an external direct product. How? Take H to be H1 cross H2, that is external direct product of H1 and H2, and phi from G to H. Define a map as phi of H1 H2 is equal to H1 comma H2. This is possible because G is H1 into H2, and each element of H1 H2 will look like H1 into H2. So before proving that this map is actually an isomorphism, we need one little observation. Suppose I take H1 in H1 and H2 in H2, then consider this element H1 H2, H1 inverse, H2 inverse. Now because H1 is normal in G, so H1 inverse H2, H1 inverse H2 will belongs to H1, and this element is also in H1, so this whole element will belongs to H1. Similarly, H2 is normal in G, so this element is in H2, so this whole element will be in H2, and this element is in H2, so whole element will be in H2. So this H1, H2, H1 inverse, H2 inverse will be in H1 intersection H2, which is identity because of internal direct product. So this is identity, mean H1, H2 is equal to H2, H1. So any element of H1 and H2 will commute. Now consider two elements of the group G, H1, H2 and G1, G2. So H1 belongs to H1, H2 belongs to H2, and G1 belongs to H1, and G2 belongs to G2. Now because H2 and H1 G1 will commute, so we can write it as phi of H1 G1, H2 G2. By definition of phi, it can be written as H1 G1 and H2 G2. And next, by definition of star, we can write it as H1 H2 star G1 G2. So this is phi of H1 H2 and phi of G1 G2. Hence phi is a group homomorphism. Now further, suppose phi of H1 H2 is equal to phi of G1 G2. So this is H1 H2 is equal to G1 G2. So by definition of coordinates, H1 should be equal to G1 and H2 should be equal to G2. So phi is 1, 1. Now again, each element of H is of the form H1 comma H2. So clearly phi of H1 H2 is H1 H2. So it means phi is a surjective. So phi is an isomorphism. So G is isomorphic to H. So it means each internal direct product can be thought of or can be written as an external direct product, and each external direct product can be thought of as an internal direct product. So I am stopping it here, the part 2. Now in the part 3, we will do the direct product of n copies and arbitrary direct product, countable copies, direct product of countable copies of group. So okay, thank you.